this is roughly 1 part per million in the case of the anomalous magnetic moment of the muon, the discrepancy. So one would say, okay, this effect would explain 1 part per million, so you could tune the couplings to explain such an effect, which is indeed possible. But to explain the effect here, this is just, it's like the Yukawa potential. You just introduce here a particle with a heavy mass. Instead of the 1 over r potential, you have e to the minus mu r divided by r, and you calculate the effect on the hydrogen spectrum. The discrepancy is 1% roughly on the proton radius, as we have seen. This is 10 to the 4th ppm. So you need to, with the same couplings, you need to explain a 1 ppm effect here and a 10 to the 4th ppm here. So obviously this is very difficult, and that's why the calculations which I've shown it, they have to involve fine-tunings. So typically, the earliest calculations here, they have invoked the exchange of hypothetical light bosons. Just to show you from one of the first papers, I think, what is shown here is the mass of this light boson in mega electron volt now, so it's capital M. And this is the effect here on the lamp shift. So this should be in milli-electron volt. So 0.3 milli-electron volt, this is what we want to explain. Now, if this light boson is too heavy, then the effect will be much too small. So this is why it drops here. And now, if you go to smaller values, the effect will rise. So you can, but you see you need to come to particles which are typically 1 mega electron volt only. And then if you want also to explain this one, these people found here these curves with this band. This explains actually the G minus 2. And they found this for, now I forget, the red curves I think was a scalar model, and the blue curves was a vector model for this particle. But roughly here in this range of 1 mega electron volt. Now, could you understand why 1 mega electron volt? It's actually, you don't need to do a real calculation to understand it. The 1 mega electron volt is roughly the product of the mass of the muon with the reduced mass of the muon with alpha electromagnetic. So, which is roughly the inverse of the Bohr radius of the muonic atom. So it's the size of the muonic atom, which is which corresponds to the inverse of the mass scale of this heavy particle. So if this heavy particle is not tuned to the size, it will not, the effect will be negligible. So that's why, so if there are such effects, you are basically constrained to having particles in the range 1 mega electron volt. Now, there have been variations on this, namely muonic forces which only couple to right-handed muons. So here you have the normal coupling is just a gamma mu term, and then you have a gamma mu 1 plus gamma 5 term, which so one only needs to tune that coupling. So, and then people have also proposed fine-tunings between, in order to explain this and that at the same time. So you introduce both vector and axial vector particles, and you make them cancel or nearly cancel here. Actually, you need to cancel 4 orders of magnitude roughly, and then you have the effect there. So it's a cancellation fine-tuning at 4 orders of magnitude. And just for the fun here, I saw that some Harvard theorists here proposed some more exotic explanation, like quantum gravity effects at Fermi scale. So it's just a few of those possible explanations, but they're, what I'd like to emphasize is they're heavily constrained by the G minus 2 of the muon, and if there is any new physics explanation, it basically forces you to explain this effect to have exchange particles which are in the range only of a mega electron volt, so which is of course not not so easy to understand. Now, I will tell you, I'm finished here for today, so I will leave this for the next lecture. So what's the next steps in this proton radius puzzle? There are several new experiments which are going on. So besides the hydrogen, people doing experiments on different targets. People redo the electronic hydrogen lamp shift measurement to much higher accuracy. People also redoing the electron scattering analysis to extract the radius with higher precision, to look back at radiative corrections and at two-photon exchange. I will come back to that in the second lecture. And several experiments are being done to extrapolate electron scattering from 10 to the minus 3 down to 10 to the minus 4 GeV squared. And so what is also on the horizon are new experiments with muons. So if there is new physics where the particles coupling to the muon, you should not only see it in the spectroscopy, but also in the scattering. So if you scatter muons precisely from a proton, you should also see deviations when you compare them with electron scattering. So such experiments have been proposed at PSI also in Switzerland, and will be done in about 3 years from now. So I will come in somewhat more detail about these things in the second lecture. So thank you very much.
I'm sure Marc will be able to entertain questions from the floor.
Yeah. In this last page, you mentioned about new experiments. For instance, in the new muonic atoms, supermassive atoms, how is the theory front? Is the theory ready to give the similar predictions and the similar accuracies and all the corrections that you mentioned?
For the
muonic
yes.
neutron and then
neutron, helium 3, helium 4. That's what. Yeah.
Yeah.
Okay. So I have slides on that, and so I will show you in the. I can show it now, of course, but I mean that's part of the next lecture.
Okay.
So indeed, just in a nutshell, so the theory is less well constrained for the reason that these hadronic corrections basically proportion to polarizability effects. And I told you that the proton is a very stiff system, so the effects are relatively small, and one knows them. The neutron is a loosely bound system. Basically, it's a pion exchange, so it has a huge polarizability. I mean, relative to its volume. So that's why, of course, in the case of neutron, there is a theory, but still one has to understand to what precision do we know this theory. And this helium 3, helium 4, so also there, if you go to light systems, the theory might be, okay, helium 4 is a quite compact system, so the whole effect is smaller, but then if you go to light atoms, which have more and more particles, then of course the theory becomes also then less accurate, I mean, to the accuracy we needed. So indeed, for these light nuclei, there's several people working on that right now. And so there, I would say, to the level of precision one needs it, there is still some work to be done. I will show you some numbers. So.
Other questions?
Could you give us some comment about actually the PSI? They have the new experiment, not new, last year, and it seemed that they also extract the magnetic radius, and the number actually is quite is very well coincide with the EP scattering. So the calculation here it seems that the magnetic radius is well, but the electric one is not. So the calculation about the two-photon exchange, yes. Do you have to worry about if you have a big effect in charge radius, then you also have a big effect in the magnetic radius. Then you will spoil the agreement between.
Okay, it's a good question also here. Indeed, there are two things. So the first is the lamp shifts means unpolarized nucleon. The lamp shift, this transition involves only the electric radius. Mm-hmm. If if you want to access the magnetic radius, you need to look at the hyperfine splitting. And because indeed people measure different hyperfine transitions, by the difference you can not only you can average, then you have the lamp shift, but you can take the difference and then you're sensitive to the hyperfine splitting. The hyperfine splitting, as you mentioned, then will give you access to the magnetic radius. And this seems to be in agreement right now. It's of course, this measurement is not with the same accuracy as for the electric radius, that's one thing, but they can access that. Now from the side of electron scattering, there's a big difference. If you, from the leading hadronic corrections to photon corrections, I will show you, on the electric form factor are quite small. When I say quite small, it's well below 1%. If you go to the magnetic form factor, which typically is obtained by a backward angle measurement, can be much larger. So these two photon corrections, so people use in electron scattering using this epsilon parameter, which is the virtual photon polarization. So forward scattering epsilon 1, these corrections vanish actually. If you go to epsilon 0, this is where you extract the magnetic radius, you have large effects. So you can still have large photon corrections in the extraction of the magnetic radius, and you will not see it in the electric radius. That's why the electric radius is much better under control in theory than for the magnetic radius. So if we see a problem in the electric radius, you will not cure it with whatever explanation you give for the magnetic. But indeed, yeah, we need to understand both.
You mentioned some new physics explanation of the photon charge radius, and one of them is to have additional Randle coupling for the muons. But since to make the anomaly cancellation to work, you need to do lots of work to
Yes, sure.
yourself.
This,
Make it very ugly.
yes, these explanations, I would say, were still plausible. I mean, but if you do some handwork, let's say, to tune until very recently. But if there is such particle, it should also not depend on what is the target, because it's basically, it's driven by the coupling to the muon. And I will show you actually that these new measurements on light atoms are already in conflict with several of these models. So just already from the point of view of just the data, it's hard, this is just to motivate that some work is going on. But these simple models, I think none of them is already able to, even with the fine-tunings, able to make sense of the existing data. So, and of course, from a theory point of view, yeah, they're not natural, let's say. But it's just, it's a very big effect, so 8 sigma, and so that's why explanations of new, unless we are really blind, so maybe we are. And, but yeah, the simple explanations are very unlikely to work.
Questions from students? I'll give priority to students. No? Any other questions from the floor? If not, I just wanted to ask one more question. Namely, how do people argue that this new particle would couple only to the muon and not the electron?
Well, it's a conjecture then. So if you let it couple to the electron, it's excluded because the G minus 2 of the electron is known to such high accuracy. So you would just, it's basically just proposed. It's not meant as a fundamental theory. It's just proposed as an effective coupling, which is only, so we don't know, there's no symmetry group, let's say, where you would say that the muons are singled out or so. So it's just proposed to have an
That sounds
effective
like
coupling.
strange.
It's, Okay, of course we don't know. If there is lepton universality, I mean, we don't know the theory. So you can just make up some effective theory where you say you propose some effective coupling, and okay, maybe by doing experiments, if one finds anything, you can try to find a pattern. So, but it's indeed it's not meant as a theory. So yeah, it's really only just as a guideline. If you would have such a particle which would couple only to muon, so what would be the size of the coupling and the mass which you would need to explain such an effect?
It's too artificial to me.
I would also consider it artificial at this point.
Okay. So any other questions? Okay, if not, let's thank Marc